Okay, so we have proved the following corollary. Recall that if I have K over F non-abelian and simple Galois extension, L over F abelian, then what it means is that these two groups can't have then, so I should just write this down, then K intersection L is just F, and the group KL over L has the same Galois group as K over F. Right? Now the point is we use this simplicity in a very important way, but it's easy if you just go back and see how the proof worked. We can actually prove the following proposition. So I've just written it out here, that even if it's not simple but almost simple, then we are still in good shape. Okay, so specifically this is relevant to the insolvability of the quintic. So same assumptions as before, I have K, F and L like before, except now I am assuming that, so L over F is still abelian, K over F I assume is it has Galois group S5. Okay, then the conclusion KL over L is finite and its Galois group is not necessarily the same as this group S5, but it can differ by just a little bit. It can either be S5 or it can be the alternating group A5. Okay, and let me just say the proof is, well, the exact same argument. We just have to use the following important property of S5, that it's almost simple. Okay, the only normal subgroups of S5 are, in addition to identity and S5, there is one additional guy which is A5. Okay, that's all you need to use. Okay, so I'm just going to leave this proof as an exercise. Just redo all the very same steps and still works for a group like S5, which is almost simple. Okay, good. And this is going to be relevant to the insolvability of the quintic. So let's prove the main theorem on the insolvability. It says that, so I stated this earlier, let f of x in Qx be such that the degree is 5 and the Galois group of f, which means it's the Galois group of its splitting field, Galois group of f is S5 or A5. Okay. Then no root of fx is expressible in terms of radicals. Okay, proof. So suppose I have a root, let alpha in C be a root of f such that alpha is expressible in terms of radicals. Okay, what does that mean? I.e., there exists a tower of fields. So what does the tower look like? So I have to take Q, which is my L0, then there is L1, L2 and so on, so till some LR, right? So that's my tower of fields. So maybe I'll just push it down a little bit. So here's my tower of fields. Okay, call this L0. Well, with what property? This tower has the following property, that each successive extension, each of these LIs is such that Li by Li minus 1 has abelian Galois group, right? This was one of our propositions, has abelian Galois group. And recall we did this by first adjoining an appropriate root of unity. So the first step was a cyclotomic extension, which of course had an abelian Galois group. All the successive steps were just simple radical extensions which had in fact cyclic Galois group. Okay, but whatever it is, every extension here has abelian Galois group. Okay, now what else are we assuming? We are assuming that, so let K be the splitting field of the given polynomial f over q. Okay, so I have a polynomial k. So let me do the following. Let me just push these, make space for k. So this is my tower of extensions, and k is the splitting field of this polynomial over the base field q. Okay, now what does that mean? I mean, how can I start using my previous proposition? We are given the following, that the Galois group, so automorphism group of k over q, is S5 or A5. So let's say, suppose it is S5. Okay, let it be S5 or A5. This is given. Now observe that how are we going to use our previous proposition? So let's see what the proposition said. It said if I have extensions in which the Galois group is S5, then I can the group KL over L, that Galois group is either S5 or A5. Okay. Now in fact this is for S5, which is almost simple. If it is actually A5, okay, if the Galois group is equal to A5, then the Galois group of KL over L is equal to A5 also, right? That's by the one corollary before this. If this is simple, then KL over L has the same Galois group. If it is almost simple like S5, then the Galois group can differ by a little bit. It became either S5 or A5. So I can actually write my proposition like this. If originally my Galois group was S5 or A5, then the composite will also have Galois group either S5 or A5. Okay, so now that allows us to make this argument a bit more compact. So what am I assuming? I am assuming that this Galois group here, k over q, is either S5 or A5. I know that this Galois group L over q is abelian. That was my assumption. Therefore, by our composites theorem, it says if you look at the composite of k and L1, okay, so let's look at the composite KL1, then KL1 over L1 is also Galois, okay, and its Galois group is either S5 or A5. Okay, so let's just mark this here. So this guy here has Galois group S5 or A5, and by our previous corollary, this also has Galois group S5 or A5. Okay, now it's perfect for an iteration. This guy here, L2 over L1, is again abelian. This parallelogram arrow here it's a Galois group, it's a Galois extension with S5 or A5 as Galois group. So again we can perform another composite. So let's look at KL1 with L2. So it's KL1 L2, that's the same as KL2 because L2 is bigger than L1. So the composite KL2, again by the same logic, because this fellow is S5 or A5 and the other one is abelian, this has to be S5 or A5. Okay, and so on. So you go all the way up till you reach the composite KLR, and you conclude that at even the topmost step there, that this extension KLR over LR has Galois group which is S5 or A5. Okay, so by iteration of this argument, what do we conclude? We conclude that the automorphism group of KLR over LR is either S5 or A5. Okay, now what did we assume about this tower? There exists a tower such that, I forgot to say this, alpha belongs to the topmost layer of this tower, right? The element alpha that we picked, which can be expressed in terms of radicals, alpha belongs to LR. Okay, now observe that what is this KLR that we are talking about here? See, K was the splitting field of the polynomial f over q. Therefore, by what we had seen earlier, the composite KLR is just a splitting field of the same polynomial, but over a larger field, over the field LR. Now, the interesting thing is this root alpha is actually already in LR. Okay, and that's an important fact. The root f has one root alpha in this field LR. Okay, so how does f split over LR, if you wish? So if the key point is here, f cannot be irreducible. F is not irreducible, definitely. F is reducible. Right? In fact, what do we know? F of x can be written as surely x minus alpha is a factor times some polynomial gx. Okay, so what is gx? Gx is a polynomial of degree 4. Now, the splitting field of f over LR, since alpha is already there in LR, you don't need to look for something that splits that. This is the same as the splitting field of G over LR. Okay, because alpha is already taken care of, that factor is taken care of. Okay, now G, however, is only a degree 4 polynomial. The degree is come down by 1, and that's going to be a problem. Okay, why? Because recall, we know something. The splitting field of a polynomial, the splitting field of the polynomial G over the base field, the degree, this extension has degree which is at most the degree of the polynomial factorial. Okay, since degree of G is 4, the splitting field of G can be at most 4 factorial degree over LR. Okay. But what do we know? We also know that the Galois group, we know this is Galois, and the Galois group is either S phi or A phi. But now here's the contradiction. Automorphism group of KLR over LR by our iteration argument was either S phi or A phi, which implies its cardinality is at least that of A phi, right? So the cardinality of the automorphism group is at least 60, which is the cardinality of A phi. Okay, but these two numbers must be the same because it's a Galois group, right? But because it's a Galois extension, so KLR over LR is Galois, implies that the degree of the extension is equal to the cardinality of the Galois group. And now that's a contradiction, because on the one hand this fellow is at most 24, and on the other hand this is at least 60. Okay, so that's a contradiction. So we have managed to show that you cannot hope to express a root of such a polynomial by means of radicals, but this still leaves open the following final question, which we'll answer, which is how does one find a polynomial whose Galois group is either S phi or A phi, right? How does one find a polynomial f in Qx such that its splitting field has Galois group over Q, which is either S phi or A phi, right? How do you find it? Okay, and now there's a little lemma which tells us when this will hold. Lemma is that if I take an irreducible polynomial, it's irreducible, degree 5, with exactly 3 real roots. Okay, the other two have some, they're complex, they have some non-zero imaginary part. If this happens, then the Galois group of this polynomial is in fact S5. Okay, so this gives you a way of constructing a polynomial whose Galois group is S5. So let's prove this. So suppose I take this such a polynomial, let's give it a name. Let me call its Galois group G. Now observe, so let alpha 1 through alpha 5 be the complex roots of this polynomial, okay, and C be the roots of this polynomial, and we'll assume that the first 3 guys are real and the other 2 are not real. Okay, so let's say that these 3 are real numbers. Okay, now the first observation, which is we know, to prove that the Galois group is S5, we will construct, elements which generate S5 inside the Galois group. So observe firstly that the Galois group, what does it do when it acts? So if we take an element of from G, then what does sigma do to any one of the alphas? Sigma must map each alpha I to one of the other alpha j's, right? Sigma permutes the roots of f necessarily. So this is our usual fact. If alpha is a root of f, sigma alpha must be a root of f. So sigma must permute the roots of f among themselves. And there are 5 roots, right? And we also know that sigma, there always exists an element of the Galois group which takes any root of f to any other root of f if f is irreducible. Okay, so given any alpha I and alpha j here, I and j between 1 and 5, so any 2 distinct guys, there always exists an element of the Galois group which maps alpha I to alpha j. And this is the other fact that we have seen before. So in terms of group actions, what this says is that, so if you recall group actions, this says that G acts transitively on the set alpha 1 to alpha 5. Okay, it always acts transitively, meaning there's only a single orbit. Therefore, by the orbit stabilizer theorem for transitive actions, this says that the cardinality of G modulo the cardinality of the stabilizer of any one element, let's say the stabilizer of alpha 1, this is just the cardinality of the orbit, okay, of alpha 1, and the orbit cardinality is 5 in this case. So this is the orbit stabilizer theorem for group actions. So what this means is that the cardinality of the group is of the form 5 times something. Okay, so this means that 5 divides the cardinality of the group. Okay, so I still don't know that G is S5, but at least I know that 5 divides the cardinality of the group. And so what can I conclude by that? This means that there exists a 5 cycle, right? So there exists an element of G with order 5. Okay, so observe that G must necessarily be, well, what else do we know? G is surely, you can think of it as a subgroup of S5 because G permutes the 5 roots. Okay, so the cardinality of G divides 120, which is the cardinality of S5, and we also know that 5 divides the cardinality of the group. Okay, so in fact, I mean the 5 silo subgroup if you wish. So what is 120? It's 24, which is 8 into 3 into 5. Okay, so since the cardinality of G can only have at most 5 power 1 as a power, and 5 definitely occurs, therefore this element of order 5, it generates in fact the 5 silo subgroup if you wish of this group G. Okay, so that surely is a 5 silo subgroup, and so we take that 5 silo subgroup or the element of that's cyclic, so we take that element there. So let's give this a name. There exists an element with order 5, so that's a 5 cycle, i.e. There exists a 5 cycle. See, what are the elements of S5 whose order is 5? So they all look like this. So they permute the 5 numbers cyclically among themselves, or 1, 3, 2, 4, 5, whatever. So anything which permutes the 5 numbers cyclically will have order 5, and those are the only numbers, only permutations with order 5. Okay, so this is the first observation about G. Now there's a second observation which comes from the fact that it's got exactly 3 real roots and 2 roots which have non-zero imaginary part. Okay, now look at these two roots, alpha 4 and alpha 5. So observe that, so this fact that if I have a polynomial with real coefficients, so in this case rational coefficients, so certainly real coefficients, then its roots occur in conjugate pairs, right? So here these 3 are of course already real, and the other 2 guys which are not real must be conjugates of each other, right? So we also know this, alpha 5 must actually be the complex conjugate of the element alpha 4. Okay, alpha phi is the complex conjugate. Now observe that we have an automorphism of C. So look at the complex numbers. The conjugation map is actually a field automorphism, if you wish. This is a field automorphism. It preserves all the operations. It's a field automorphism of C. Okay, and its identity is, this map is of course identity on R and therefore on C, on Q, sorry. Okay, now so what you do is you restrict this conjugation map to K. So you restrict the conjugation map to the splitting field K. K is just Q alpha phi. Now what does this conjugation map do? Well, it fixes alpha 1, 2 and 3, right? So this map behaves like this on the roots. It sends these to themselves and it interchanges these two guys, alpha 4 and 5, alpha 4, alpha 5. Okay, now what sort of element is this? If you think of in terms of the group action on these 5 elements, this is like a transposition, right? i.e. this acts as follows. It's like it sends the first 3 elements to themselves and it transposes the 4th and the 5th elements, right? So there exists a transposition in your group G. So the group G has two kinds of elements. It's got a 5 cycle and a transposition, and this is now a fact about the symmetric group S5 that you need. These 2 elements generate S5. Okay, S5 is generated by any pair sigma tau, where sigma is a 5 cycle and tau is a transposition. Okay, so with this fact, one is more or less done, because now a corollary. So let's accept this without proof. It's rather easy to prove this. Now what this implies is that G contains both a 5 cycle and a transposition, so there is no other way out. It's got to be the entire group S5. Okay, and finally, what are examples of so there is always so we have a nice criterion here. What sort of polynomials will have this property? You just need to look for something which is irreducible and has 3 real roots, right? So to do irreducibility, you could look for things. You can use the Eisenstein's criterion. So let me just give you 2 examples of polynomials which have this property. Fifth, it's got degree 5, and this is irreducible because you can use Eisenstein's criterion with p equals 2. The one below is irreducible by using Eisenstein with p equal to 3. Okay, and to check that they have only 3 real roots, what you could maybe do is sort of look at the graph of the polynomials. Okay, so just graph the polynomial, and of course that's probably not a completely foolproof thing, but you can check that it's got only 3 real roots. Okay, so such a graph will look like this, right? So it's got 1 real root, 2 real roots and 3 real roots. So if it's monic, then it's like this. Okay, or you can take derivatives and so on. So any which way. So here are examples now of the polynomials which no matter how hard you try, you cannot write the roots of this polynomial using radicals.